Algebra 2. This is 721, which is simplifying radical expressions. So hopefully you're following along with the handout or the PDF. We're going to skip over the warm-up. So the objective is to simplify radical expressions until all perfect powers are removed from the radicand. So in the last two sections, in 713 and then a little bit in 712 and maybe even 711, we were dealing with radical expressions that were perfect roots, and the exponents inside were perfect multiples of the root. And in this section, they won't be. So when we try to take those roots, we're going to have something left over. And so the issue there is, what do we do with those leftovers, and how do we express that, and how do we write that? Now, that brings us to the idea of irrational numbers. Irrational numbers are numbers that are not a perfect square, and the root can only be approximated by decimals that never terminate or repeat. So, for example, if I take out my calculator and I try to do, let's see, if I turn this on and I try to do the square root of 4, we know that's a perfect root and we get 2. But if we try to do something like the square root of 5, that's not a perfect root, and we get a long decimal, and this decimal actually goes on for infinity and it never ends. So when we come across a situation like this, if we have to take the square root of 5 and we're trying to work through things in our radical, we would actually leave 5 inside the radical and continue our operations there, rather than writing out this long decimal and trying to do operations on this long decimal. So that's the whole point of this lesson, is figuring out when you come across stuff that doesn't work out perfectly and then leaving it inside your radicals. The first rule that we want to talk about is the product property of radicals, and that's something that's going to help us deal with these things. And so what the product property of radicals says is that if you have the nth root of sum A times sum B, if these two things are multiplied together, then if it makes it easier on you, you can split them up into separate radicals that are multiplied together. The key is that your root cannot change. So if this is the third root, it has to remain the third root the whole way through. If this is a square root, it has to remain a square root the whole way through. But you can write them under separate roots and have them separate radical signs and have them multiplied together. In some cases, you'll come across some problems that will be easier to work with in this format, and then there'll be others that will be easier to work with in this format. Now, so I've kind of come up with a way of dealing with some of these, and I call it the outside and the inside rule. So we know that we normally write our root on the outside, and then we can have things on the inside like a, and like let's say a, and it's raised to an exponent, and that exponent is on the inside. So how we can deal with this is we can take what's on the inside divided by, that's a division sign, divided by our root on the outside, and that's going to give us our new out remainder new in. Okay, so this might seem really weird to you right now, but this kind of division is the same kind of division that you would do in third grade. When you came across a remainder, we're not going to go ahead and find a decimal approximation with it. We would just do, an answer might be something like 2 remainder 3. So let's do a quick example. Let's say we have the fourth root of x to the 9th. Okay, so how we would deal with this is I would do in divided by out. So what I have on the inside is 9, and what I have on the outside is 4. And if I do 9 divided by 4, I get 2 remainder 1. So then that means my answer is x squared, because look at that. The first number is your new exponent on the outside, and then times the fourth root of x to the 1. And if your exponent is 1, you don't have to write it. okay? So I'll write this a little bit cleaner without all the arrows. It becomes x squared times the fourth root of x to the 1. So you want to make it clear that this is a fourth root, and your 4 is inside your radical sign, and then your exponent of 2 really is an exponent, and that's attached to the x, and sometimes it's good to leave a little bit of a gap. So if you were to have the fourth root of x to the 9th and simplify it, this is what your answer would be, okay? So we did in divided by out, so 9 divided by 4, that's my 9 divided by 4, and 9 divided by 4 is 2 remainder in. So new out, remainder new in. So 2 is my new exponent on the outside, right? So my 2 shows up here. And then 1 is my new exponent on the inside of the radical. So 1 and 1. And your root never changes. So your root is 4 the whole way through the problem. And one way that I always remembered that is, if you think about the roots of your family or the roots of a tree, those never go away. Those never change, right? If you cut down a tree, the roots are still going to be there, okay? And your grandmother's always your grandmother, okay? Those things never change. So the root of the radical always stays the same, okay? So we can go through some of the examples in the packet. Let's see. So let's see. If I do some of those examples on that first page right there, so one of the first ones you were given was the fourth root of 32 x to the 7th. Okay? Now, with numbers, sometimes with numbers, it's really helpful to think of the largest perfect roots inside of that number. Okay? So, for example, maybe it would be good for us to make a list and have this to use with all of the problems that we're going to do. So we know that we might need some square roots, and we'll fill those in later. And we know we might need some cube roots, and we can fill those in later. And we know that we might need some fourth roots, and we'll fill those in later. We'll fill those in right now. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256, 5 to the 4th, I don't know that one off the top of my head. Let's see. 5 to the 4th is 625. 6 to the 4th is 1296. I think that's good enough for now. Okay. So, 32. How are we going to find the fourth root of 32? So what you can do is you can use your list and take 32 and cut it in half. Okay? So, let me see. So this is what I would think to myself. So I would say half of 32 is 16. So then I go back to my list, and that's where I start on my list, okay? So half of 32 is 16, so I start at 16 and I work backwards. So, well, lucky for us, 16 is actually on the list, and so I work backwards and I say, well, is 16 a factor of 32? It is, okay? So 16 is a factor of 32. So then one of the ways that we could rewrite this is the fourth root of 16 times 2, okay? Because 16 times 2 is 32. And then we still have x to the 7th, okay? So let's go ahead and break this down a little bit further. Now, the fourth root of 16 is 2, right? And how do I know that? Well, because we figured that out when we did our list. The fourth root of 16 is 2, because, and the other reason is, well, you know, 2 to the 4th is 16, so that's how I know the fourth root of 16 is 2. I'm just going backwards from that. So then I would have a 2 on the outside, okay, because the fourth root of 16, that turns into a 2, and we pull that on the outside. We still have my fourth root. this 2, I can't take the 4th root of this 2, so that stays on the outside. Now, to deal with this x to the 7th, we'll come down here, and we'll do a little thinking, okay? We take our exponent on the inside, which is 7, and we're going to divide it by our root on the outside. So I'm doing in divided by out, okay? And so 7 divided by 4 is 1 remainder 3. So that gives me new out remainder new in. So what that means is 1 is my new exponent on x on the outside, right? So on the outside I have x to the 1. If your exponent is 1, you don't have to write it. And then 3 is my new exponent on x on the inside. So then on the inside I have an x cubed, okay? And I've left this giant gap here. Well, I don't have to. You can leave it there and, your answer is still fine. We can kind of close things up a little bit. And this is 2x times the 4th root of 2x cubed. Right? And so that's your answer to that example. So let's do some more of these. Let's see. So if I go on to the next page, let's see. So now I'm into your classwork. Okay, so for number 1, I have the square root of x to the 4th, y to the 6th, and z to the 7th. Well, it's going to be easy to deal with my x and my y, because these exponents we can just divide by 2. So 4 divided by 2 is 2, so you get an x squared. 6 divided by 2 is 3, so we get a y cubed. Now for the 7, so to deal with the z, we would do 7 divided by 2, right? Because when you're taking a square root, you always divide your exponents by 2, and that gives us 3 remainder 1. So then that means, so this 3 means we have a z with an exponent of 3 on the outside, and this 1 means we have a lonely z raised with an exponent of 1, or no exponent needed, on the inside. So then this is your entire answer. So you need everything on the outside that you were able to evaluate perfectly, and then your leftovers on the inside. Okay? So for number 2, we have the square root of 98 times a to the 4th, b to the 6th. Alright, so that 98. Well, 98, we're trying to find the square root of 98, so let's make our square root list. So let's see, we're going to have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, right? So I'm going to square all of these numbers, and I'll get 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and 169, right? So those are all my perfect squares. And I'm trying to find the square root of 98. So the first thing you do is you figure out what half of that is, okay? So half of 98, we'll just do 98 divided by 2, and that gives us 49. So then you go to your list, and you find 49 on your list. Well, lucky for us, 49 is a perfect square, okay? The square root of 49 is 7. So then we can use that 49. So instead of writing this as 98, we're going to write this as 2 times 49, right? 98 is the same thing as 2 times 49. And then we have a to the 4th, b to the 6th, okay? Now, we can't take the square root of 2. That's as far as that number goes, so we leave that on the inside. The square root of 49 is 7, so we can pull that out. And then for the square root of a to the 4th, well, we just divide that exponent of 4 by 2, so that'll give us an a squared on the outside. And then for the square root of b to the 6th, we divide that exponent by 2, so that gives us b cubed on the outside. And so we don't have anything left over on the inside, so we've got 7a squared b cubed root 2. Okay? So let's take a look at number 3. So for number 3, I have root 50 x y to the 6th z to the 9th. Okay, so 50 we know is not a perfect square, so we start off with what is half of 50? Half of 50 is 25. Okay, so then we check our list. Well, lucky for us, 25 is on the list. So then we can go ahead and rewrite 50 as 25 times 2. And then we still have x, y to the 6th, z to the 9th. Alright, so now, well, what's the square root of 25? That's 5, so I can pull that on the outside. The square root of 2 we can't do, so we leave that on the outside. Now, the square root of x to the 1. So, there's an exponent on this x, you just can't see it. That exponent is 1, right? And then we have a root over here, we just can't see it. That root is 2. So, if we've got an exponent of 1 and a root of 2. Okay, an exponent of 1 and a root of 2. Whenever your exponent is smaller than your root, you don't have to do any division. You don't have to figure anything out. This all just stays on the inside. So I'm going to say that again. When your exponent is smaller than your root, you don't do anything. You leave it on the inside. So that x to the 1 stays on the inside. Now, the y to the 6th, well, that's a perfect power of 2. So we do 6 divided by 2, and we get 3. So we have a y cubed on the outside. Now, for the z to the 9th, so for that, okay, so for the z, I'm going to do 9 divided by 2, which is 4, remainder 1. So I have z to the 4th on the outside, a z to the 1 on the inside, and so my answer is 5y cubed z to the 4th times the square root of 2xz, so the whole thing. Alright, let's take a look at number 4. So for number 4, we have 75 x cubed y to the 4th z to the 6th. Okay, now, so for this one, so again we say to ourselves, well, what is half of 75? So half of 75, I can't do that off the top of my head, so I'm going to go to my calculator. 75 divided by 2 is 37.5. Okay, so that doesn't work out as nice as the other one. So this is how we do it. So half of 75 is 37.5. So I go to my list and I figure out, well, where would 37.5 be? Okay, so 37.5 would be somewhere here between 36 and 49. Okay, so then what I do is I work backwards going up the list, and I stop at each perfect square and I ask myself, is that a factor of 75? So working backwards, so the first one I come across is 36. Is 36 a factor of 75? No. Okay. Is 25 a factor of 75? Yes, it is. So then we can rewrite 75 as 25 times 3. And then we still have x cubed y to the 4th z to the 6th. Alright, so the square root of 25 is 5. We can pull that out. We can't do the square root of 3, so we're going to have to keep that on the inside. Now, the square root of x cubed, so to do that, I'm going to do 3, my exponent on the inside of 3, divided by my root that I can't see, but I know it's 2. So 3 divided by 2 is 1 remainder 1. So that means I have an x to the 1 on the inside and an x to the 1, or I'm sorry, an x to the 1 on the outside and an x to the 1 on the inside. And then for y, well, that's easy. 4 divided by 2 is 2, so I'll have a y squared on the outside. And then for z, I do 6 divided by 2 is 3, so then I'll have a z cubed on the outside. And then I'm left with just my 3x on the inside, and that whole thing is your answer. So, number 5, the problem that they give us is the square root of negative 16 x to the 5th. Okay? So that is no solution because you can't take the square root of a negative number. And then the same thing for number 6. They give us the square root of negative x cubed y to the 6th, and again, you can't take the square root of that negative number, so that is no solution. Okay, so going on to number 7. So for number 7, we have the square root of x to the 5th, y to the 7th, z to the 9th. Okay, so 5, 7, and 9, none of those are perfect multiples of 2, so we're going to have to divide all of those by 2 and deal with our remainders. So for x, we'll do 5 divided by 2, which is 2, remainder 1. So that means we have an x squared on the outside and a lonely x to the 1 on the inside. For y, we'll do 7 divided by 2, which will give us 3, remainder 1. So I'll have a y cubed on the outside and a y on the inside. And then for z, I'll do 9 divided by 2, which is 4, remainder 1. So then I'll have a z to the 4th on the outside and a z to the 1 on the inside. And you've dealt with everything, and that's your answer. Okay, so going on to number 8. So for number 8 and 9, I don't know why they included those in this section, but those are perfect multiples of 2, so we can go through those really quickly. So for number 8, I have the square root of x to the 6th, y to the 8th, z to the 4th. Okay, so for all of these, I can divide these numbers just by 2 and everything works out perfectly. So 6 divided by 2 is 3, so I'll have x cubed. 8 divided by 2 is 4, so I'll have y to the 4th. And then 4 divided by 2 is 2, and so I'll have z squared. And then for number 9, that's the same deal. I've got the square root of x to the 6th, z to the 12th. So 6 divided by 2 is 3, so I'll have x cubed, and then 12 divided by 2 is 6, and so I'll have z to the 6th. So moving on to number 10. So number 10 has more going on. I have the square root of 192 x, y to the 7th, z to the 10th. Alright, so let's deal with that 192. So half of 192, I don't know that off the top of my head, so I'm just going to go to my calculator and do 192 divided by 2, and I get 96. Okay, so let's look at our list. So 96 on our list would be somewhere right here between the 100 and the 81. Okay, so we start here and we work our way backwards. So at each number we ask ourselves, well, is 81 a factor of 192? So is 81 a factor of 192? So let's do 192 divided by 81. Nope, it's not. Okay, 64. Is 64 a factor of 192? So I go to my calculator and I do 192 divided by 64. Yes, it is. So that works out. So then I can rewrite 192 as 64 times 3. Okay, and then I copy everything else down. So I have x, y to the 7th, z to the 10th. So now I can deal with these piece by piece. Okay, so the square root of 64 I know is 8, so I can pull that out. Let's see. The square root of 3, well, I can't do that, so that stays on the inside. And that x, that's just an x to the first power, so we can't do anything about that. So we'll have to leave that on the inside because that exponent is smaller than a root of 2. And then for y to the 7th, so for that y, I'm going to do 7 divided by 2, right? My exponent on the inside divided by my root on the outside, and that gives me 3, remainder 1. So that means I'll have a y cubed on the outside and a lonely y to the 1 on the inside. And then for z to the 10th, well, 10 divided by 2 is 5. So then I have z to the 5th on the outside. I don't need anything on the inside for z. And then there's my answer there. For number 11, I have the square root of 128 x cubed, y to the 5th, z to the 6th. Okay, so for 128, well, we want to figure out what half of that is. So half of 128 is 64, okay? And that's nice because 64, if we look at our list of perfect squares, 64 is a perfect square. So we can just rewrite 128 as 64. I don't know why I went all the way over there. We can just rewrite it as 64 times 2, and then I have x cubed, y to the 5th, and then z to the 6th. I'm just gonna, okay, try again. So 128, 64 times 2, and then x cubed, y to the 5th, z to the 6th. Okay, now the square root of 64 we can do. That's just 8, so I pull that out. The square root of 2, I can't do that, so that has to stay on the inside. Square root of x cubed, well, to deal with that, I'm going to do 3 divided by 2, which is 1 remainder 1, so then I have an x to the 1 on the outside and an x to the 1 on the inside. For my y to the 5th, I'm going to do 5 divided by 2, which is 2 remainder 1, so then I have a y squared on the outside and a y on the inside. And then for z to the 6th, well, that's a perfect power, or a perfect multiple of 2. So 6 divided by 2 is 3, so then I just have z cubed on the outside, and I don't need anything else for z on the inside, so then this whole thing is my answer. Okay, so let's take a look at number 12. So for 12, well, this is a cube root, so that means we're going to be dividing all of our exponents by 3, and we've got to think about cube roots. So for 12, I have the cube root of 8x to the 6th, y to the 9th, z to the 10th. Okay, now 8 is a perfect cube, and it would probably be good for us to list some of our perfect cubes. We'll just do a few for now because we don't need very many. So if I just go 1, 2, 3. And we can use this list in later lessons, and it would probably be good for you to make a list or memorize these. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is, 4 times 4 is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, okay? So, going back to this, well, the cube root of 8 is one of the first ones that we listed. The cube root of 8 is just 2. So, we can pull that out right off the bat, okay? And then x to the 6th, well, that one is also easy to do because 6 is a perfect multiple of 3, so I could do 6 divided by 3, and that gives me 2. So I can pull out an x squared, and then the same thing for y to the 9th. 9 divided by 3 is just 3, so then I would have y cubed. Now, the z to the 10th is a little tricky. So for that one, okay, to deal with z, I would do 10 divided by 3, which gives me 3 remainder 1. So, okay, so I did 10 divided by 3, which gives me 3 remainder 1. So that means I have a z cubed on the outside, and then a z left over on the inside. And so, there's my answer there, and those are all of the classwork problems.